race to win wars and explore the stars, have created some of the most fantastic products ever designed, and we use them every day, unaware of their amazing origins. On Wicked Inventions. Parachutes, extreme sport equipment that was refined during World War II. Rockets, the Nazi technology that put a man on the moon. Solar panels, NASA know-how that harnesses the power of the sun. We reveal the amazing science and manufacture behind these wicked inventions. Parachuting today has become the pastime of thrill seekers and has become a sport in itself. But how did these life-saving devices develop, and what role did war have to play in their advancement and evolution from a tool of safety to one of leisure? Records of parachute designs date back as far as the 13th century, with an anonymous manuscript from Renaissance Italy showing designs of a free-hanging man clutching onto a conical canopy. Soon after, Leonardo da Vinci sketched his own designs.
Da Vinci's parachute had poles 7 meters long, and a pyramid-shaped structure, and made out of cotton for the actual parachute itself. It was tested by a skydiver, Adrian Nicholas. He used it from 3,000 meters in the air, and he said it was actually quite a nice parachute. It worked quite well.
The term parachute was first used much later, in the 18th century, when Louis-Sébastien Lenormand sketched a device that resembles those of today and made the first successful public jump using his designs. So, how do parachutes actually work?
What the parachute acts as is a bigger surface area to slow down your terminal velocity. You're still going to fall, you're still going to go towards the ground, but a parachute works by acting as a big surface area to slow you down.
The eve of World War I accelerated the development and mass use of the parachute and saw its adoption within the military. First adopted by the Germans, artillery observers tethered to observation balloons would use parachutes to escape in the event of being shot down by fighter aircraft. Although they weren't widely used by aircraft during the First World War, some examples could be found in the German air service. Although the added weight did impede the performance of the aircraft, the parachutes were not particularly effective and many pilots died using them. By World War II though, the materials and designs of parachutes had greatly improved, and they became an integral part in the battle for Europe and the Pacific.
Churchill decided to train up 5,000 new parachute jumpers, and this was the birth of the parachute regiment. And they were first used tactically in 1941 when 38 men were parachuted into southern Italy, and that was the start of what we would see as the tactical use of parachutists to infiltrate enemy territory.
After the war, with surplus parachutes left over, along with the many highly trained airborne forces, returning soldiers began to use the parachute for leisure. Today, parachute designs have become more and more advanced, with skilled jumpers able to perform complex maneuvers in increasingly extreme circumstances, giving the parachute a new dual purpose of providing practical safety as well as white-knuckle excitement. Performance Designs are a leading manufacturer of parachute canopies based in Florida.
Performance Designs started in 1982 with the idea of building a better parachute, better in terms of flying better, opening better, landing better, more fun to fly. The production of a parachute is a fairly complicated process involving first inspecting the materials and making sure that they're correct for our needs, and then cutting the material to precise shapes, reinforcing the parachute with various types of tapes, nylon tapes, and then sewing it together in a very accurate way to make sure that the parachute has the shape that it needs. Time may be as little as maybe 11, 12 hours, as many as 100 hours, depending on the model.
The production of these state-of-the-art parachute canopies begins with the receiving of all the materials required. Everything that comes into the receiving department goes through visual inspection and extensive testing before being distributed to the production floor. Fabric tests being performed include strength testing, UV testing, fabric durability testing, and permeability testing. 2 hydraulic testers test the tensile strength of the fabrics, lines, and tapes. There are 2 light tables for visual inspection of the fabric. Here the operator will look for any imperfections and place a sticker on these, which the laser cutter machine will then avoid, ensuring that no imperfect materials are used. Once materials are approved, the first phase of production begins at the custom-built laser tables. The tables suck air down through small holes in order to hold the fabric in place, while the laser cuts it. The software goes through a nesting process that selects all the parts to be cut and lays them out in the most efficient manner, like puzzle pieces, to reduce the amount of fabric wasted. The laser table also encodes the serial number, part number, model, and size of each part. This allows production to keep track of all the parts and for identification of the canopy after it's assembled. The laser table also makes small match marks, which tell the sewers where the pieces match up. They are then sent to the production floor, where everything is inspected again before sewing begins.
The fabric is very strong. We still need to strategically reinforce that fabric in certain areas to provide a strong attachment point, say for the suspension lines to be attached. This is done in the form of narrow, what they call narrow fabric, which we think of as nylon tapes. We have several different widths and strengths that we put on the parachute fabric in different areas, and that serves to reinforce the parachute and also to make sure that it holds its shape properly. In the prep department, we also apply the warning label, which gives information about the precise characteristics of the canopy in terms of how much weight you can put under it, who it's for.
Next, the canopy parts are sewn together. Each cell of a canopy is made up of a top skin, a bottom skin, and ribs. First, the top skin, bottom skin, and non-load bearing ribs are sewn together in a process called I-beaming. Then the top seam is completed by sewing together the top skin and loaded ribs, which joins the cells into one big piece. Load-bearing ribs are the ones that will have lines attached to them, and non-load-bearing ribs will not. After the top seam is complete, the bottom seam is added, which ties together the reinforcement tapes that will function as the parachute's skeletal structure. The trailing edge is then sewn together. This job is called tail seaming, after which the fabric part of the canopy is basically complete. One main element that's missing is the lines. At the rigging station, the canopy will meet its line set and slider that have already been prepared. The lines are attached to the canopy through tabs and then bar tacked into place using a bar tacking machine. Before the finished parachute can leave the factory, it is inspected again. The parachutes are inspected a total of 5 times throughout production due to their life-saving nature, to ensure the chances of failure are minuscule. Inspecting is taken very seriously, and every inch of the canopies will be covered. Once complete, the parachute canopy is ready to take to the skies. The parachute, truly a wicked invention. Think of a rocket and we instantly picture the finale to a celebration, or a vehicle for putting a satellite into orbit. But the rocket has more uses than you can imagine, and its development is intertwined with warfare. The origins of the rocket can be reliably traced to China. In 1232, at the Battle of Kai Keng, the Chinese repelled the Mongols with a barrage of arrows of flying fire. A tube capped at one end contained gunpowder. The other end was left open and the tube was attached to a long stick. When the powder was ignited, the rapid burning of the powder produced fire, smoke and gas that escaped out of the open end and produced a thrust. So, the rocket race had begun. But how do rockets actually work?
So a solid fuel rocket propulsion system basically requires a fluid of some sort to be pushed out the back of the system, and then the system which is pushing it will move forward. This is because of Newton's third law. Every action has an equal and opposite reaction. So what happens is, as the fluid is being pushed out, that pushes back on the engine, and that pushing back on the engine is what moves the rocket forwards.
The early rocket's effectiveness in battle can be debated, but it certainly made an impression on the Mongols, and they brought the technology to Europe as Genghis Khan cut a swathe through its eastern territories. From the medieval period onwards, rockets were a source of fascination, with numerous experiments and fanciful weapons planned, which achieved varying degrees of success. It would be World War II, however, that would see the catalyst in the development of rocket technology that would one day see a man on the moon. By the end of the war in 1945, the increasingly desperate German military had managed to develop the V-2 rocket that was used to attack London. Unlike the early solid-fuel gunpowder rockets, the V-2 was liquid-fueled, burning 1 ton of its liquid oxygen and alcohol fuel mix every 7 seconds. This created a far more efficient rocket, as its thrust could be regulated by controlling the fuel flow. Arriving too late in the war to be a decisive weapon, its designers would still play a major part in the post-war space race between Russia and the United States.
After World War II, the Americans had a missile and space program which was very different from what we know today. It was run in the military, so it was run by the Air Force, the Navy and the Army. But the most famous component of that program was the work of Wernher von Braun and his fellow German rocket scientists, who took the knowledge that they'd developed in the Second World War building the V-2 to pave the way for what eventually became the heavy Saturn moon rockets of the 1960s.
The Saturn rockets had to be large for a reason. To escape the gravitational force of the Earth and reach space, a rocket needs to be travelling at over 25,000 miles per hour, or 7 miles per second. To achieve this and carry a payload, the rocket has to generate an enormous amount of thrust, and this required a mind-boggling 960,000 gallons of fuel for every launch. With 5 engines firing on ignition, the Saturn V rocket left the launch pad with 7.6 million pounds of thrust, pushing the Apollo astronauts into orbit. Von Braun's design was amazingly powerful, but it was also very clever.
Perhaps the biggest challenge in developing a space rocket is actually building a multi-stage rocket, because you can't realistically carry all the fuel that you'd need from the ground to space for your whole launch. So you split the process into several stages, and the first stage just carries the fuel that it needs. This has made realistic spaceflight possible. The downside is, of course, that you have to have more engines, because you have to have engines in each stage, so that increases the possibility of other things going wrong.
The Saturn V rocket may be the largest, heaviest and most powerful rocket the world has ever seen, but it still shares the same power principle as a firework that you can fire yourself.
So a firework uses the perchlorates and nitrates in the fuel to mix, and that provides the oxygen when it's heated. So those two can burn together. You have the fuel, you have the jets coming out the back, which is the fire and the smoke that you often see. And with the rockets such as those that used to be the space shuttle and all the rockets supplying the International Space Station, they burn typically hydrogen and oxygen, because in space there is no oxygen, so they have to carry all elements of the fuel. And they pretty much just chuck it out the back, and that chucking out the back pushes this system forward, so you have propulsion.
Invented hundreds of years ago, able to put men on the moon or entertain children on a cold dark night, the rocket is truly a wicked invention. The quest to put man into space may have cost billions of dollars and taken years for Russia and America to achieve, but we're going to show you how you can become a rocket-owning power in your own right, albeit on a micro level, with the power of a matchstick. Okay, so it won't quite get to the moon, but it is still fun. The materials you'll need: matchsticks, a ruler, wooden skewers, a barbecue lighter, paper clips, a pair of scissors, a pen, sticking tape, pliers, and last but not least, aluminium foil. To begin, take a matchstick and carefully cut off the head with your pliers. Next, cut a rectangular piece of aluminium foil 6 cm long and 12 cm wide. Then cut off one of the corners. Lay the cutout sheet flat and place the matchstick head on one of the shorter ends, approximately 2 cm from the top. Fold over the foil slightly and place the skewer below the matchstick head, like so. Now, carefully roll the foil into a tube as tightly and neatly as possible. Any gaps could be disastrous. Once complete, pinch the foil above the match head and twist into a tight point. Next, add sticking tape to the bottom of your foil rocket on either side. These will help your rocket effortlessly glide through the skies. Impressive stuff. Now, the launch pad. Take one paper clip, Now bend and twist it until you have a metal spike with a loop. Find something stable and sticky to push your new paperclip launch pad into. We found that the duct tape works great. Place the rocket onto the launch pad and you're almost ready for liftoff. The only missing ingredient is the ignition system. Grab your barbecue lighter and you're sorted. Literally don't try this in your own home. Always fire the rocket outside and never aim at anyone or anything combustible. Or if you have a large warehouse handy, like our fancy tester, that'll do fine. Spark that lighter and hold it under the rocket so it gets nice and hot. And after, well, quite a few misfires, we have blast off. Like a real space rocket, the fuel, in this case the match head, combusts, creating thrust in the form of gas molecules that rush out of the bottom of the foil tube. And in keeping with Newton's law that every action has an equal and opposite reaction, results in the tiny tin rocket flying off the skewer. Congratulations, you've now entered the space race. Although a bit late, and on a very small scale. The concern over dwindling fossil fuel supplies and climate change have led to an explosion into the research, development and use of renewable energy. But did you know that the solar panels attached to our rooftops actually have a connection to space exploration? It all starts with solar power. The photovoltaic effect is the phenomenon of electrons in a substance being excited into a higher state of energy when they are hit by photons of light, allowing them to act as charge carriers for an electric current. Many materials, such as silicon, possess these photovoltaic properties. So, where does NASA fit in? With fossil fuels a cheap and abundant power source, the interest in solar cells faded in the early 20th century. And it was not until man decided to explore the stars that this method of power found a demand. NASA's need for powering its spacecraft, satellites and space stations from a never-ending supply of energy harvested from the sun has seen the organisation work with commercial partners to continually research and design increasingly lighter and more efficient solar panels. So, how do these super solar panels work?
Before light gets into the solar panel, you have to have an anti-reflective coating, which means that you don't send half the light you're trying to get back out by reflecting it. So most solar panels will appear very dull to look at and not reflective. This allows light to get passed through the first layer and be trapped within the second layer, which is often a semiconductor made of silicon. It can be done with boron, can be done with gallium, and all sorts of small metals to alter the properties of the semiconductor. Light comes in, you have photons, which are small packets of energy, and each photon is a bit of light. Each of these hits an atom, and when it hits an atom, the electrons on the outer side of the atom are excited. They go into a slightly more energetic state. When this happens, it's possible for those electrons to move from one atom to another, and this is what you want to generate electricity, because electricity is the movement of electrons.
With NASA continuing their research and development of solar cell technology, the future looks bright for solar electricity. So, the next time you see a rooftop adorned with a solar panel or two, thank space exploration for developing yet another wicked invention. PowerFilm are an Iowa-based manufacturer of flexible, thin-film solar panels that provide custom solar products for industrial, consumer and military remote power applications. First, the solar material must be produced.
The basic roll processing, where we make the core solar module, begins with a roll of plastic, a very thin roll. Tends to be somewhere around 30 microns thick and maybe 1,000 feet long. That roll goes through a sequence of deposition machines to put down first a back metal contact, followed by the semiconductor amorphous silicon, actually 6 layers of amorphous silicon, which makes the solar cell itself. That's the part that absorbs the light and turns it into electricity. And then a top conductive layer that is also transparent, lets the light in, but also is conductive enough to bring the electricity out the front face. So you have the metal on the back, the transparent conductor on the front. That's where you get the power out.
From here, the film is then loaded onto a laser scribing machine. Here, the roll is unwound on a machine that uses laser heads to scribe the material into sections that begin to make up the individual solar cells on the roll. From here, the rolls are moved onto the printing stage. Electrical insulators are printed between the individual solar cells. in order to isolate the positive and negative sections, as well as also being run through a silver print machine. The silver print machine prints conductive silver ink particles that increase electrical conductivity.
Once it's been tested, it goes through a process where a copper bus bar is put on, which is something we will solder to get the electrical connections later. Then a laminate is put on the front surface and the back surface, and that's usually a Teflon type product that is highly resistant to chemicals and water, moisture. It will protect the module from the environment.
The roll is then loaded into a die cutting machine. This machine unwinds the roll and die cuts it into individual modules which can be used in a variety of products. The die-cut modules are then loaded into a machine that tests each module electrically, one at a time. The machine places each module onto a lighted surface, and probes check electrical characteristics. The modules are then sorted into pass and fail bins. Passing modules are then loaded into a large machine called a pick and place. Here, a robotic arm picks up individual modules, checks them for orientation, and then places them onto a fabric surface. The robot keeps placing modules on a fabric in a pattern that has been determined by the computer. Once completed, a laser cuts the fabric piece, forming the outline of the foldable solar panel. Panels are taken from the pick and place station, and operators then string the modules together on the fabric body using a flexible, multi-stranded wire known as a Litz wire. The steps here include using a soldering iron to burn away small sections of lamination over the conductive tape. Multiple connections are made to ensure that the solar panels are still operational, even if a wire breaks.
Once that is all done, we will then run it through a lamination process, through a high heat lamination process, which helps bond everything together, helps reseal so that the moisture resistance is improved.
The panels are then moved to the sewing cell. Here the edges of the panels are sewn. With the edges of the panels sewn, a top fabric wrap is added. Product labels are stitched on and strips are sewn over the wire attachment points. In the finishing cell, the operator adds a circuit board and connector. Grommets are added to the corners, which allows the user to strap down the panel in windy conditions. Completed units are then taken outdoors for a final test prior to packaging. Passing units are then packaged and moved to the shipping department in cases, ready to provide unlimited solar energy across the globe. Solar panels, truly a wicked invention. So there you have it, a dash through the hidden history, super science and amazing manufacture of products that you use every day, but have never realised their amazing background. Parachutes, rockets and solar panels, all wicked inventions.